So in the last lecture, we looked at a little bit of basics in terms of mathematics, right? We looked at trigonometry, we looked at vectors, we looked at PEMDAS, stuff like that. And we also talked a little bit about units and unit conversion. So today in this lecture, we're going to be focusing on kinematics in one dimension. So kinematics is how we describe the motion of objects without referring to the forces that are acting on them, right? So colloquially, we can think of them as how things move, right? If we're talking about physics, it stands to reason that we're going to need to talk about, things and where they are, how fast they're going, how fast they're accelerating, and stuff like that. And so that's going to be the topic of today's lecture. The reason why we're talking about 1D motion here is because you can't really get any simpler than one dimension. So one-dimensional motion is something moving along a line, right? You can either go forward or backwards. And so we're going to be focusing on that stuff today. So since we're talking about things in motion, right? Since we're talking about kinematics, a good place to start would be talking about positions, right? Because if we're talking about the motion of objects, well, it doesn't really make sense to talk about motion without first mentioning position, because motion is just changing positions. So here I've drawn an x-axis, right? And we're going to need to label our starting point. So this spot right here, we're going to call x is equal to 0. Now, if we want to describe the position on this x-axis, we're going to need to use vectors. So typically in physics, we describe the position of something by a vector. So let me actually just switch this. So I've switched over to my paper having dots in it because I'd like to indicate positions as marked out by these little notches. Right, so this is x equal to 1, x is equal to 2, and so on and so forth. And in the opposite direction, we have x is equal to -1, -2, so on and so forth. And so if we want to describe the position on this x-axis, right, in our coordinate system, then what we need to do is we need to have a vector that starts from the origin, this 0 point, and it points to wherever, what position we want to indicate. So let's say that we're trying to indicate that something is at position x is equal to 2. So we can draw a vector, points from x is equal to 0, to x is equal to 2. So let's call this position vector x. And since it's pointing to something at x is equal to 2, we denote that by saying that this vector x is equal to 2 x hat. Labeling this as a vector is almost unnecessary since we're only working in one direction, right? It's not like we're working with an x and y coordinate system. There's only 2 ways to go. You can either go forwards or you can go backwards, right? So if we want to describe something in one dimension like this, we can represent the direction of the vector by a positive or a negative sign. So if I told you that the position of something on this coordinate system, say that we have this vector A, it's equal to 3. I'm kind of being a little sloppy by leaving off the hat here, but since we're working in one dimension, this lets us indicate that the position here for this vector A is located right here. So this vector A points from the origin to x is equal to 3. Just like this. This is our vector A. And the fact that this sign is positive, right, since the fact that A is equal to +3 indicates that we're moving to the right +3 units, right? If you want to describe something that's in the negative x direction, then we could say, well, there's a vector B that's at, well, I don't know, -2. And that would be right here. Right there. So normally when you're working in 2 dimensions or higher, but I think for our purposes, we're only going to be working in 1 or 2 dimensions in this course. But when you're working in 2 dimensions or above, it does make sense to write the notation out like this, where you indicate both its x and y components. But since we're only working in 1 dimension, the direction of the vector is specified by saying whether or not you're pointing to the right of x is equal to 0, or whether or not you're pointing to the left of x is equal to 0. So even though I'm writing these vectors down like this. And you know what? Maybe I will just include the hats. Just to be consistent. Even though we're writing the vectors down like this, the positive and negative sign indicates what direction we're going in. And the number indicates how far we are going in that direction. So since we've just talked about positions on this x-axis, on this one-dimensional coordinate system, as represented by vectors, now we can go on to define something called the displacement. So the displacement is defined as, delta x, or delta whatever, is equal to the final position of your object minus the initial position of your object. Here, this is called x naught. This little zero here is a naught, and this indicates where your starting position was. So let's say we have a coordinate system. Let me just redraw this coordinate system here. Switch over to something like this. Here's our x-axis. Let's say that this is x is equal to 0 right here. All right, so this is x is equal to 1, 2, 3, so on and so forth. And this is -1, -2, so on and so forth. So let's say that our starting position, I'm going to mark it in blue, is x is equal to 1. So our starting position for this is x is equal to 1. You switch over to this. And let's say that our final position is x is equal to 3. So according to how we've defined our displacement, the displacement of our object, whatever it is equal to our final position minus our initial position. So we can actually calculate the displacement here. Our displacement, delta x, is equal to our final position, which is x is equal to 3, minus our initial position, which is x is equal to 1. So in this case, our displacement is 2 units, which indicates that we've gone 2 units to the right. So we started here, and we ended up going here, and this little red vector here is our displacement. So, like I just mentioned, displacement is a vector. Not only does it have a magnitude, right, how far you've gone, but it also has a direction. So in this case, a positive displacement indicates that you have moved to the right. So since our final position is x is equal to 3, and our initial position is x is equal to 1, it makes sense that we've gone 2 units to the right since we started here, and we ended up here. So here I've drawn a little track. It's this circular region here. So let's say that the start and finish line are right here. So this is the starting line, but it's also the finish line. And let's say that this track has a length. So the track has a length of, well, I don't know, 800 meters. I don't really know track and field stuff so well, so I'm not sure if an 800-meter track is an appropriate length for a track, but let's just say it is for our purposes here. So the question I want to ask you guys, if you start at the starting line and you run all the way around the track, right? You run around all 800 meters and you get back to the finish line. The question is, what is our displacement? All right, start at the finish. We start at the starting line. We run all the way around the track until we get right back to where we started. What's our displacement? So keep in mind that this is still a one-dimensional problem because when we're running on the track, we only have 2 directions that we can go. We can either go forward or we can go backwards. So in this case, we say that going forward is, positive displacement, going backwards is negative displacement. Now the thing is, if we're describing our position on this track by a vector, right, a vector that points to where we are on the track, then the way that we define our displacement here, in this particular case, is our final position minus our initial position, but our final position is right where we ended up to begin with. Since the starting line and the finish line are the same place, our final position is where we started. And our initial position is just our initial position. So you see that if you run around this track once, you have ran a distance of 800 meters, but your displacement, which is a vector quantity, is 0. More specifically, 0 meters. Got to remember the units. So this is an example of the difference between displacement and distance. We have run a distance or walked a distance of 800 meters. We have gone around this once. We've gone a distance of 800 meters, but our displacement, which is defined as the difference between where we started and where we ended, is 0. So a little later on, we'll see examples of differences between displacements and distances. So you guys will get a pretty good idea of this stuff. So since we just talked about displacement and position and distances and stuff like that, the next logical step is to talk about speeds and velocities. So to begin with, let's talk about the average speed. Average speed. So the average speed is defined as the distance traveled, not the displacement, but the distance traveled, divided by the elapsed time. Right. So notice here that the average speed, which is equal to the distance divided by the elapsed time, is a scalar quantity. Right? There's no vectors anywhere in here. Distance is just a number, and the elapsed time is also just a number. Neither of these are vector quantities, and so the average speed, which is just a scalar divided by a scalar, is itself a scalar quantity, right? The average speed is just a number. So here's a nice little example to demonstrate average speed. So the example is this. A car travels from Albany, New York to New York City, a distance of 200 miles in 3 hours. What is the average speed of the car in meters per second? So the first thing that we need to do, we need to write down the definition for the average speed. So in this case, the average speed is equal to the distance traveled, which in this case is 200 miles. 200 miles divided by the elapsed time, or how long it takes to actually do that. So in this case, that is 3 hours. So 3 hours. Now, the problem wants the average speed, not in miles per hour, but in meters per second. So we're going to need to do a little bit of unit conversion, right? Game back. We need to do a little bit of unit conversion to take 200 miles divided by 3 hours and turn it into something in meters per second. So we need to know the relationship between meters and miles, first of all. So we know that 1 mile is equal to 1,609.3 meters. And I will never ask you guys to remember stuff like this. When this comes up on the exam on Friday, I will not force you guys to remember this. I will have a little equation sheet for you guys. So don't worry about stuff like that. I'll never ask you to remember, unit conversions like this. So we know that 1 mile is equal to 1,609.3 meters. So we also know that 1 hour is equal to 60 minutes. And last but not least, we know that 1 minute is equal to 60 seconds. So If we take this first equation and we divide both sides by 1 mile, we get that 1 is equal to 1,609.3 meters divided by 1 mile is equal to 1. So we're going to multiply our average speed by 1,609.3 meters divided by 1 mile. And so notice here that the miles up top get canceled by the miles on the bottom. So the units of the miles cancel out. And now we're left with an answer in meters per hour, which is good, but we can simplify a little bit more. Let me just move this over so I have enough room to write. And so next up, we're going to use the second equation to transform from hours into minutes. So in this case, we're going to want to divide both sides by 60 minutes. So on the left-hand side, we're going to have 1 hour divided by 60 minutes is equal to 1. And so we're going to multiply our average speed now by this quantity. So we have 1 hour divided by 60 minutes. Right. So the hours on the bottom get canceled by the hours up top. And we're left with a current answer in meters per minutes. And finally, we need to use this last equation to convert from minutes to seconds. So if we divide both sides of this last equation by 60 seconds, we get that 1 minute divided by 60 seconds is equal to 1. Then we can multiply our average speed by this quantity, right? 1 minute divided by 60 seconds. And so the units of minutes get canceled out. And so now we're left with an answer in terms of meters per second, which is exactly what the problem wanted. And so now when you multiply all this stuff together, you get an answer. So the average speed ends up being equal to 29.8 meters per second. Just like that. So now that we looked at average speed, let's look at its companion, average velocity. So average velocity is defined as the displacement divided by the elapsed time. Elapsed time. And so in symbols, the displacement is delta x is a vector divided by the elapsed time, which we say is delta t. And here, when I say delta t, it means the change in time. So that's going to be the time elapsed minus your starting time. But in this course, what we're going to usually do is say that, well, we're starting our watch at t is equal to 0 seconds. So you have t minus 0 here. So in our cases, we're just usually going to take delta t to be equal to t. So delta t, the elapsed time, is just going to be equal to t. Okay. And so our average velocity then becomes that delta x, which is defined as our displacement. So it's going to be our final position minus our initial position divided by our elapsed time, which, as we just mentioned, we're starting our clocks at time t is equal to 0. So the elapsed time is just t. So in the last part, I pointed out that the average speed was a scalar because, you know, the average speed is defined as the distance elapsed, or the distance traveled divided by the elapsed time. And both of those were scalar quantities. They were both numbers. Now, in our case, the average velocity is defined as the displacement divided by the elapsed time. So because this quantity here, this displacement, is a vector, right? It's really two vectors, the final position minus the initial position. The average velocity itself is in fact a vector. So we're going to see how this affects things going forward in an example that I'm about to show you guys. So here I've written down our second example, which says that a car travels from Albany, New York to New York City, and then returns back to Albany for a total round trip distance of 400 miles. And it does all of this in 6 hours. So the problem wants us to find the average speed and the average velocity in units of meters per second. So to begin with, let's look at the average speed. So the average speed is equal to the distance traveled divided by the elapsed time. Right, which in this case, the distance traveled is the round trip distance of 400 miles. 400 miles. And the elapsed time is 6 hours. 6 hours. Right. But notice that we can divide both 400 and 6 by 2. So the average speed then becomes, if we pull a factor of 2 out of 400, we get 400, which is equal to 2 times 200 miles. And in the denominator, if we pull a factor of 2 out of the 6, we get 2 times 3 hours. So that's equal to 6. So the 2's cancel out. And it turns out the average speed is equal to 200 miles in 3 hours. But this is actually what we solved in the previous example. So it turns out the 200 miles in 3 hours is equal to, what is it, 29.8 meters per second. So this is our average speed. Average speed. All right, so that's one part of the problem. Now the next part of the problem is asking us to find the average velocity. So the average velocity, like we just mentioned, is equal to the displacement divided by the elapsed time. Now the thing is, our initial starting point and our final ending point are both the same, right? We started from Albany, we went to New York City, and then we finally returned back to Albany. So our displacement here, our final position minus our initial position, is going to be 0 because we started and ended in the same spot. So 0 divided by anything is going to be 0. So it turns out that our average velocity is equal to 0 meters per second. Right. And that's the answer to this example. So in the first part of this lecture, we talked about positions, distances, displacements. And in the previous section that we just talked about, we talked about velocities. We talked about average velocity and average speeds. And so now a natural next step is to talk about accelerations. So the average acceleration of an object, is equal to its change in its velocity, which I denote by this delta symbol and this vector v for velocity. So it's the change in an object's velocity divided by the elapsed time. So expanding this out, our change in velocity is our final velocity minus our initial velocity, right? Both of which are vector quantities, divided by the elapsed time, which we call t. So just like the average velocity was a vector, the average acceleration, which is the change in velocities divided by the elapsed time, is also a vector, right? It has a magnitude and it has a direction. So something I want to talk about that really helped me out when I was learning physics is the relationship between positions, velocities, and accelerations. So if you guys just take away one thing from today's lecture, I want it to be this. It's important. So accelerations change velocities. And velocities change positions. All right, so if you guys can remember this, you'll be golden. There we go. So what does this mean? So if an object has a velocity, that means it's moving, right? Colloquially, we can think of velocities as moving. So the velocity means that its position is changing. If you're on the highway and you're traveling forward at 50 miles per hour, well, that means that you're going down the highway at 50 miles per hour. You're moving. Your position is changing. And accelerations kind of do the same thing, but for velocities. So if an object that's traveling with some speed, right, maybe it's traveling at 0 velocity, that is, it's not moving, or maybe it's traveling at 50 miles per hour, whatever. If something that has some velocity experiences an acceleration, then that velocity will change. So you can be driving down the highway at 50 miles per hour, and if you start accelerating forward, right, that means you're starting to drive faster, you're speeding up. Your velocity is changing, right? Maybe you started at 50 miles per hour, but then you accelerated a little bit, and now you're traveling at 55 miles per hour. Or maybe you're like me and you drive a little too fast on the highway. So accelerations change velocities, and velocities change positions. So everything we learned about prior to this point in this lecture was mostly definitions, right? We learned how to define the position of something by using a vector on a one-dimensional coordinate system. We learned how to define the velocity, average velocity, and we learned how to define the average speed. And then we learned how to define the average acceleration. And so now I'd like to focus on something slightly different. I'd like to look at special cases where we restrict ourselves to looking at our particular physical situation and then seeing what we can derive out of that. So the first situation I want to talk about are called constant velocity equations, where we presume that our object is moving at a constant velocity, and we see what we can build from that. So just to start with, equation 1 says that the velocity, which we denote by some vector v, is equal to some constant. Now remember, since we're in a 1D coordinate system, our vectors are really just given by numbers because positive or negative indicates what direction you're traveling in. And so the number indicates the magnitude of the vector. Okay, so if this is our first equation, right? Then let's see what we can get by assuming a constant velocity for our object. Whatever our object is, it's going at a constant velocity. Let's see what we can get from that. Well, if we look at our definition for acceleration, or average acceleration, our average acceleration, which I'm going to denote by A, is equal to the change in our velocity divided by the change in our elapsed time, delta t. So writing this out, we have our final velocity minus our initial velocity. In the numerator and in the denominator, we have delta t. But if our velocity is constant, it's not changing. So the velocity that we start with and the velocity that we end with are exactly the same, which means that acceleration is our final velocity, which it turns out is also equal to our initial velocity, minus our initial velocity divided by the elapsed time is equal to 0, because the top part is 0. So overall, our average acceleration in this case is 0 meters per second squared. So this is the second equation for our constant velocity equations. Equation number 2. If our object is moving with constant velocity, that means the acceleration must be 0. Which isn't unusual, because if you guys remember in the last part that we just talked about, I said that accelerations change velocities and velocities change positions. So if the velocity is not changing, then it stands to reason that there's no acceleration with which to change it, right? So I hope that makes a little bit of sense. And last but not least, let's look at the definition for velocity. So the velocity is equal to the change in your position, or the displacement, divided by the elapsed time. And so the displacement up top in the numerator of this is given by our final position minus our initial position divided by delta t, the elapsed time, which is t. And so if we multiply both sides of this equation by t, we get v times t is equal to x minus x naught, our final position minus our initial position. And the last but not least, if we add our initial position, x naught, to both sides, we get our final position is equal to our initial position plus our velocity times time. So this is our third and final equation when it comes to constant velocity equations. So equation number 3 says that our final position is equal to our initial position plus our velocity times time. So some of you might notice that the constant velocity equations that we derived last time, we derived using the fact that the acceleration was equal to 0, right? We got that by noting that if the velocity is constant, that means there must not be any acceleration, so the acceleration is 0. So this is an example of a constant acceleration problem, right? Except in this case, the acceleration just happens to be a special value, which is 0. So in this case, let's look at constant accelerations which are not 0, not necessarily 0. So to begin with, if our acceleration is a constant, and you'll notice that I'm going to drop the vector notations because in one dimension, we really just treat our vectors as numbers and the direction we indicate with a sign. So for 1D motion and 1D motion only, I'm going to drop the vector hat notation. So when we're looking at constant acceleration problems, if our acceleration is constant, let's look at the consequences of this. So by the definition of acceleration, we have that the acceleration is equal to the change in velocity divided by the change in time. So the change in velocity is the final velocity minus the initial velocity. And the change in time, or the elapsed time, it's going to be t. But if our acceleration is constant, then what we can do is we can multiply both sides of this equation by t, much like we did similarly in the previous part with the constant velocity stuff. So if we multiply both sides of this equation by t, we get that the acceleration times time is equal to our final velocity minus our initial velocity. And then if we add the initial velocity to both sides of this equation, we get that for our first equation, our final velocity is equal to our initial velocity plus our acceleration times time. So this is our first constant acceleration equation. And so if you guys remember what I said about accelerations changing velocities, well, this is a good example of it. So here we have our final velocity, which is equal to our initial velocity, right? So our final velocity is how fast we end up going. And it makes sense that our final velocity is equal to how fast we initially started, plus how much we accelerated during that time. So if our acceleration is 0, that is, if we don't have this term here, right? If that's 0, then our final velocity is simply equal to our initial velocity. And that's how we get the constant velocity equations in the previous section. So our second constant acceleration equation, is that our displacement, delta x, is equal to 1/2 times our initial velocity plus our final velocity multiplied by time. So this here is our second constant acceleration equation. And now let's look what happens when we take our first equation and we plug it in to the second equation, right? So our first equation tells us how to find final velocity in response to constant acceleration. And we can take this final velocity and plug it in to our second equation right here. So let's do that. So our third constant acceleration equation, when we take equation 1 and plug it into equation 2, we get on the left-hand side, the displacement x is equal to 1/2 times our initial velocity plus our final velocity, but we're going to use equation 1 here. So equation 1 says that our final velocity is equal to our initial velocity, v0, plus our acceleration times time. So all of this is multiplied by time right here. And so now let's simplify. So on the right-hand side, we have 1/2. And then we have our initial velocity plus our initial velocity. So this is going to be 2 times our initial velocity plus our acceleration times time. And all of this is going to be multiplied by time. So if I multiply through by 1/2 and multiply through by time, t, the equation that we end up getting says that our displacement, delta x, is equal to our initial velocity times time plus 1/2 times our acceleration times time squared. And notice that our left-hand side here is our displacement, but we can define the displacement as our final position minus our initial position, right? And then the right-hand side stays the same. And so if I add the initial position to both sides, we get our third and final, but our third equation, which says that our position is equal to our initial starting position plus our initial velocity times time plus 1/2 times our constant acceleration times time squared. So this is our third constant acceleration equation. So our fourth and final constant acceleration equation, we can obtain by taking equation 1 and solving it for t, and then plugging it into equation 3 down here. Now, that's actually a rather long derivation, and I kind of don't want to do that. It's just a lot of algebra, but you guys should trust but verify. So, on your own time, you guys should try and solve equation 1 for t, and then plug it into the third equation whenever you see a t, and see if you can't derive what I'm about to show you guys here. So our fourth and final constant acceleration equation says that our final velocity squared minus our initial velocity squared is equal to 2 times our acceleration times our displacement delta x. So this is our fourth and final constant acceleration equation. And we got all of these by just assuming that the acceleration was constant and by using the definitions for velocity and acceleration. Isn't that neat? So now let's look at an example to sort of help us get used to the equations that we just saw. I know there's a lot of them, but this will sort of help. So this example says that a car accelerates uniformly from rest and attains a velocity of 100 meters per second in 10 seconds. So find the acceleration of the car, the average velocity of the car, and the displacement of the car after those 10 seconds. So we're going to start solving this by writing down what we know given from the problem. So the problem says that a car accelerates uniformly from rest. So this is a constant acceleration problem. And if a car or an object starts from rest, that means that its initial velocity is 0. So its initial velocity is 0 meters per second. And the problem says it attains a final velocity of 100 meters per second. So its final velocity is 100 meters per second. And it does all of this in a time span of 10 seconds. So our time t is 10 seconds. The problem wants us to find the acceleration of the car. So we need to find A. It wants us to find the average velocity of the car. So V average. And it also wants us to find the displacement after those 10 seconds, right? So let's start by using equation 1 to help us figure out what the acceleration of this car is. So equation 1 says that our final velocity is equal to our initial velocity plus our acceleration times time. And so notice that we have the final velocity, we have our final velocity, we have our initial velocity, and we have the time, right? We have our final velocity, our initial velocity, and the time. And the only thing that we're missing is the thing that we're trying to solve for. So let's solve for it. Let me just zoom out a little bit. So on the left-hand side, we have our final velocity, which is 100 meters per second. 100 meters per second. And that's equal to our initial velocity, which is 0 meters per second. Okay, that's pretty easy. Plus our acceleration, the thing we're trying to solve for, times time, which is 10 seconds. Well, 0 plus anything is just going to be equal to whatever that other thing was, right? Adding by 0 doesn't really change the quantity that we're adding it to. So this is just going to be equal to the acceleration times 10 seconds. So we have 100 meters per second on the left-hand side, and our acceleration times time on the right-hand side. So now I'm going to divide both sides by 10 seconds to get the acceleration, which is equal to 100 meters per second divided by 10 seconds. This is going to give us an acceleration of 10 meters per second squared. All right, so this is the first part of the problem. Now for the next part of the problem, I'm going to hold off on solving for V average, and I'm instead going to solve for the displacement. So we can solve for the displacement by using our second constant acceleration equation, right? Which says that our displacement delta x is equal to 1/2 times our initial velocity plus our final velocity times time. So we already have our initial velocity, our final velocity, and our time. So let's just plug all this stuff in to find our displacement. So our displacement delta x is equal to 1/2 times our initial velocity, which is 0 meters per second, plus our final velocity, which is 100 meters per second, times time. So the elapsed time this thing was accelerating was 10 seconds. So we put a 10 there. And so 0 plus 100 is 100. So we're going to have 1/2 times 100 times 10. So 100 times 10 is 1,000. Multiplied by 1/2 is 500. So over the course of this 10 seconds, our displacement is 500 meters. There we go. So that's the second part of the problem. And for our third and final part of the problem, we want to find the average velocity of this car over the course of this 10 seconds. So by the definition of V average, the average velocity is equal to the displacement divided by the elapsed time. Now, we just found our displacement. It's 500 meters. So we put 500 meters in the numerator. We divide by the elapsed time, which is 10 seconds. And so we get an average velocity of 500 divided by 10, which is 50 meters per second. So V average, our average velocity, is 50 meters per second. And that's the whole problem. So I've got one more example to show you guys regarding constant acceleration problems. So the problem is this. A car is traveling at 20 meters per second, and the driver sees the traffic light turn red. After 0.93 seconds, the driver applies the brakes and the car decelerates at 7 meters per second squared. Now the question is, what is the stopping distance of the car as measured from when the driver saw the red light? So this is really a two-part problem. In the first part of the problem, the driver sees the traffic light turn red, but they're not yet braking. They haven't applied the brakes yet, right? That only happens after 0.93 seconds. The second half of the problem is when the driver applies the brakes and the car starts decelerating at 7 meters per second squared. So the first part of the problem is a constant velocity problem, right? Because there's no acceleration yet. And then the second half of the problem is a constant acceleration problem where the car is now decelerating at 7 meters per second squared. So if the question is asking what the stopping distance of the car is, as measured from when the driver saw the light, the problem is asking us to find the total distance that the driver goes, or the total displacement of the car from when the driver sees the red light. Right? So let's start solving this by writing down what we know. A car is initially traveling at 20 meters per second. So the initial velocity of this car is 20 meters per second. And the driver sees the traffic light turn red. After 0.93 seconds, so let's say that the first amount of elapsed time is 0.93 seconds. So after this amount of time, the driver applies the brakes and the car begins to decelerate at 7 meters per second squared. So here we have our acceleration. Now, if the car is traveling at 20 meters per second, this is a positive number, which indicates that it's traveling to the right. Now, if the car is decelerating, that means it's slowing down. So this indicates that our acceleration must be minus 7 meters per second squared, right? So really quickly, the reason for this is because if we look at our first constant acceleration equation, we have our final velocity. It's equal to our initial velocity plus our acceleration times time. Then notice that our final velocity is equal to our initial velocity, which in this case is 20 meters per second, plus our acceleration times time. So let's think about it this way. Time is positive, right? We're considering time to be positive. Our initial velocity is positive. And if we have our acceleration be equal to plus 7 meters per second squared, then that means that our final velocity is equal to some positive number plus another positive number. That is, our final velocity would be bigger than our initial velocity. Now, the problem with that is the driver is slowing down. So the only way that the driver can slow down, in this case, is if our acceleration is negative. So that's my justification for why we need this negative sign here. Okay. So what else does this problem tell us? So what is the stopping distance of the car? Okay, it doesn't tell us that much more. So let's say that the total distance traveled, or the total displacement traveled by this, let's call it x total, is equal to x1 plus x2. So x1 is the distance that the car travels during the first part of the problem before it started braking, and x2 is the distance traveled by the car after the driver starts applying the brakes and the car starts decelerating. So to begin with, let's try and solve for the distance traveled in the first part of the problem before the cars started to brake. So we know from our constant velocity equations that the distance traveled is equal to where we started, our position of where we started, plus our initial velocity times time. Now, we're going to assume that the moment that the driver sees the traffic light, we're going to call that position x is equal to 0. So the driver's initial position is equal to 0, right? Because we're going to say x naught is equal to 0 here. And so the distance traveled in the first part of the problem is just equal to the initial velocity times how long that person was traveling like that for. So that distance is equal to the initial velocity, which is 20 meters per second, times the length of time that person was traveling at that velocity for, which in this case is 0.93 seconds. So that time is t1. So this is 0.93 seconds. So this gives us a distance of 18.6 meters. So now for the second half of the problem, let's figure out how far the driver goes after applying the brakes. So to do that, I'm going to make use of our fourth constant acceleration equation, which says that our final velocity squared minus our initial velocity squared is equal to 2 times our acceleration times our displacement. So let's look at this now. The final velocity of this car should be 0 because the car is coming to a stop. So by coming to a stop, it's not moving, which means its final velocity is 0. So we have 0 meters per second squared minus the initial velocity, which was 20 meters per second. We're going to square that. Then on the right, we have 2 times the acceleration of the car, which is minus 7 meters per second squared. Finally, we have delta x, which is our displacement. That's how far the driver goes after braking. Right. So on the left-hand side, we have 0 squared, which is 0, minus 20 squared, which is 400. So the left-hand side becomes minus 400 meters squared, second squared, right? Because when you square a quantity, you're also squaring the units of that quantity. So the right-hand side is going to be 2 times negative 7. So this is going to be negative 14. Negative 14 meters per second squared times delta x. So now if I divide both sides by negative 14, we get that the displacement for the second half of the problem, which is really our x2 value that I mentioned earlier, this displacement is going to be equal to 28.6 meters, roughly. 28.6 meters. Right. And so now the total distance traveled by the car, right, after the driver sees the red light, is equal to the distance traveled before they apply the brakes, which is 18.6 meters. 18.6 meters, plus the distance traveled after the driver applies the brakes, which we just found to be 28.6 meters, for a total distance traveled of 47.2 meters. And that's the answer to the problem. It's a little bit more involved, and we used a couple different equations. But that wasn't too bad, right? So in the last part of this lecture, I want to talk about something called free fall, which is a special example of constant acceleration motion where the acceleration is caused by gravity. So it's important to note here that the acceleration, or the magnitude of the acceleration, caused by gravity on the surface of the Earth, so we'll say that the magnitude of the acceleration caused by gravity on the surface of the Earth has a special value. We call it g. And this has a magnitude of 9.8 meters per second squared. And the acceleration due to gravity is always pointed towards the center of the Earth. So it's important to note that this value, which is the acceleration due to gravity at the surface of the Earth, and that's important, the surface of the Earth, is not super precise. And the reason for that is because as you go further away from the Earth in general, the acceleration due to gravity gets weaker. So the acceleration due to gravity would probably be a little bit less than 9.8. And as you get further and further and further away from the Earth, right? If you leave the solar system, then the acceleration due to gravity is going to be very, 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 very small. But that's more of an extreme limit. Additionally, the Earth is not a perfect sphere. So it's not like you're the same distance away from the center of the Earth as you are at the North Pole as when you're standing on the equator. And because of that, the acceleration due to gravity is going to change depending on where you're standing on Earth as well. So, but in all cases, the acceleration due to gravity generally points towards the center of the Earth. And that's pretty much all we need to know right now. So when describing free fall problems, we're typically going to use a coordinate system oriented in the y direction. So this is our y-axis. And it's still a one-dimensional problem, right? Because we're either going up or going down. And those are really the only two directions that we can go. And so we define the positive y direction to be up. So I'm going to say that this point is y is equal to 0, for example. And by going up, our y values are positive. So this might be, y is equal to 1 meter, and so on and so forth as you go up. And anything below this point is a negative value. So if you're going down, those positions are negative. And so since our acceleration due to gravity is pointing towards the center of the Earth, it's always pointing down. So our acceleration in problems like these is going to be equal to minus 9.8 meters per second squared in the y direction, right? So it generally points downwards. But again, in one-dimensional motion, I'm generally going to drop the vector notation stuff. So I'm just going to say that the acceleration due to gravity is just minus 9.8 meters per second squared, right? Where this minus sign indicates that we're pointing down. So let's look at a problem that deals with free fall. All right, so here's a free fall example that I've cooked up for you guys. So in this example, it says that a ball is thrown down from the top of a 300-meter building with an initial velocity of 2 meters per second. The problem wants us to find the time it takes for the ball to hit the ground and the velocity of the ball when it hits the ground. So let's start writing down the stuff that we know. Well, the initial height of the building is 300 meters. And the ball is thrown downwards with an initial velocity of 2 meters per second. So the initial velocity of the ball, v naught, is going to be minus 2 meters per second. Right? If this were positive 2 meters per second, that means we're throwing the ball upwards. But since we're throwing the ball downwards, it gets that minus sign. So the problem wants us to figure out the time it takes for the ball to hit the ground and its velocity when it hits the ground. So, oh yes, one last piece of information. The acceleration, since this is a free fall problem, it's going to be minus 9.8 meters per second squared. Right? And we're trying to find the time it takes for this ball to hit the ground and its final velocity just the instant before it hits the ground. Okay, so we're going to say that the ground is at a height of 0. And so the building is at a height of 300 meters above that point. So our final height for the ball is going to be 0. But we know how to calculate the position of something when we know its initial position, its initial velocity, and its acceleration. Right? This was one of the constant acceleration equations that we looked at earlier. So this is equal to y naught plus v naught t plus 1/2 at squared. Right? So the only thing that's different between this and the constant acceleration equations that we saw before is that instead of talking about things going in the x direction, I'm now talking about things going vertically in the y direction, but they're exactly the same otherwise. So on the left-hand side, the final height of this ball is 0. And so let's start plugging things in on the right-hand side. So on the left-hand side, we have a final height of this ball when it hits the ground. which is 0 meters. On the right, we have its initial starting height above the ground, which the problem tells us is on top of this 300-meter building. And it has an initial velocity of -2 meters per second. And now for time here, I'm going to put t star, right? And I'll explain that in a second. But moving on, the additional terms are +1/2 times the acceleration, which is -9.8 meters per second squared, times the time squared again. So we're going to do t star squared. All right, so why have I put this t star here? Well, the reason I've put this t star here is because t star is the amount of time it takes for this ball to actually hit the ground, right? In general, we don't have this 0 here. We just have the final position of the ball is equal to its initial position plus the velocity times time plus 1/2 times a, or the acceleration times time squared. So I'm saying that t star is equal to the amount of time it takes for the ball to hit the ground. All right, so we're going to try and solve this equation for t star, because that's what part A of this problem is asking us to find. I need to scroll down a little bit because I'm going to need some room. So bear with me here, but I'm going to try and put this equation right here, into a special form. So I'm going to multiply -9.8 by 1/2. So it's going to be -4.9. And then I'm going to multiply everything by -1. I'm going to move some stuff around. So if you guys have any questions about this, just let me know. So on the left-hand side, I'm going to have 4.9 meters per second squared times t star squared plus 2 meters per second times t star minus 300 meters is equal to 0 meters, right? And you might be like, well, why did you do that? Well, this equation actually has a name. This is called the quadratic equation. So whenever you have an equation that looks like some number a times x squared plus some number b times x plus some number c is equal to 0, this is called the quadratic equation. And so there's a way to solve this equation, right? There's certain values of x where when you plug them in, that makes the left-hand side of this equation equal to 0, which makes this equation true. So how do we actually solve for those values of x? Well, to do that, we need to use something called, very creatively, the quadratic formula. Can you guess how it got its name? So the quadratic formula says that the values of x which satisfy this equation is equal to minus the value of b plus or minus square root of b squared minus 4 times the value of a times the value of c, all divided by 2 times a. Right? So if you take this hot nonsense and you plug it into the quadratic equation, you'll find that the left-hand side will be equal to 0, which is what we call solving the equation in this case. So again, this is called the quadratic formula. Right? And it might come up from time to time as we do problems. So the reason why I even bring this stuff up is because the quadratic equation that I've written down here is exactly the same form as the thing that we're looking at here. So this equation is what we're trying to solve, right? And we're trying to solve for t star. We're trying to solve for the amount of time it takes for the ball to hit the ground. So notice that we just compare the coefficients. So we have the thing multiplying our variable squared. So our value of a is 4.9. Our value of b is whatever's being multiplied by the variable just to the power of 1. In this case, that is 2. And then our variable, or excuse me, our value for c is just this minus 300 here. So let's write that down. So for our purposes, a is 4.9, b is equal to 2, and c is equal to minus 300. Now, if we take these numbers and we plug them into the quadratic formula, we're going to get two solutions. So let's go about doing that. So t star is equal to minus b, so minus 2 plus or minus the square root of b squared. So b is 2, so it's 2 squared, minus 4 times our value of a times our value of c. So look at this. This is all divided by 2 times our value of a, which looks like that. Okay. So let's do some simplifying. First things first, let's clean up this thing in the square root. So 2 squared is 4, and 4 times 4.9 times negative 300 is minus 5,880. So this minus sign cancels with the negative sign in the minus 300. So probably easier just for me to write it down. So this is equal to negative 2 plus or minus square root 5,884. And all of this is divided by 2 times 4.9 is 9.8. And it's here I want to bring our attention to this plus and minus sign, right? This plus or minus sign that shows up in the quadratic formula comes about because you can either take the plus sign and plug, the resulting x thing in, and it'll solve the equation, or you can use the minus sign. Whichever sign you use is still a solution to this quadratic equation. Now, the problem is this doesn't always give physically realizable results. So let's see what I mean by that. So we have t star is equal to minus 2 plus or minus. So the square root of 5,884 is equal to 76.7, about 76.7. And all this is divided by 9.8. So now let's look carefully. In the numerator, we have minus 2 plus or minus 76.7. So let's take the case where we take the positive sign, right? We take the plus sign. So if we have t star equal to negative 2 plus 76.7, well, that's going to be a positive number, right? Because 76.7 is much bigger than negative 2. In fact, this top thing will be 74.7. So we'll have some positive number divided by some positive number, in which case our total answer for our time is going to be a positive number, right? Which is good. That makes sense. But what if we had used the minus sign here? So the minus sign solution to t star would have also solved this equation, which is good. But the problem is you'll have minus 2 minus 76.7. So overall, we're going to have a very negative number on top and a positive number in the denominator. So overall, our time will be negative, which isn't very physical. because that means we'll need to have traveled backwards in time to achieve this solution. But we start our watches as soon as we drop that ball from the top of the building. So our time here has to be positive, in which case we need our time, T star, to be positive. So we have to take the plus sign on grounds of being physically real. So this becomes -2 plus 76.7 divided by 9.8. Right, so -2 plus 76.7 is 74.7. Dividing all of that by 9.8. So this is equal to 7.62 seconds. 7.62 seconds. Right, so the amount of time it takes for this ball to hit the ground is 7.62 seconds. And with that, we've solved the first half of the problem. Right, so the amount of time it takes for the ball to hit the ground, a little less than 8 seconds. Now for part 2, it's really not too bad. So the second part of this problem is asking us to find the velocity of the ball just before it hits the ground. And we can do that by using the constant acceleration equation that says that the velocity is equal to, or the final velocity is equal to the initial velocity plus our acceleration times time. And so we know what our initial velocity is. That's -2 meters per second, plus our acceleration, which is the acceleration due to gravity. So that's going to be -9.8 meters per second squared. And we figured out how long it takes the ball to reach the ground. That's 7.62 seconds. Right. And so putting this all together, if you were to put this into a calculator, this will tell you that the velocity of the ball just before it hits the ground is about 76.7 meters per second. And with that, we've solved the second half of the problem. It's not too bad, right? I'll see you guys tomorrow.